slide you can see here. So you don't need to log in from here to via WebEx. Okay, so please don't log in via X in this room. Okay, because of the Wi-Fi maybe congestion. And the second thing is that so we have a few mics, and it's really sensitive. This means that every chat, every typing sound, everything is captured. So be careful. Okay. There is no mute button, unfortunately. Only this one has a mute button.
Okay, everybody take your hand.
Yeah, and don't say anything bad about your neighbor across the way.
Okay, so and after this session, we decide whether we should go back to the main hall for the afternoon session. But still, they have been working for the tuning, and so if they couldn't, they cannot fix the problem, then for the afternoon session as well as this session, you can stay here or there to join the afternoon session. But everything will be decided after this session. Okay. So after this session, we'll have a lunch break. But before, to eliminate some confusion, before starting lunching session, not lunching session, before starting lunch, we decided to the location whether we can attend from here or from there. Okay. Okay, so are you ready to be silent? Okay. So okay, let's start. The first session is soft paper. The title is the evolution of distributed data set synchronization solutions in NDN. Let's see. Actually, I cannot see my webpage. So the author is Philipp, Moll, Varun, Patil, Wang, and Lixia, Zhang. So who presents this session?
Varun.
Okay, so please start.
Yeah, so I hope that the remote people can hear me. Please let me know if that's not the case. And so I'm going to be presenting this work. Let me just start my timer because I don't have one here. This work on the Sync SOK paper that we did at UCLA and Memphis. And so we sort of, this is sort of a systematization paper on Sync in general. So everything you need to know about Sync, you might find it here. So before I start, I want to just quickly say a note about why do we need transport protocols in the first place. The answer to this is twofold. The first one is that our network layer that we build, any network layer, has to be minimal. And the reason is obvious, that we have to deploy this everywhere. Every device has to run this network layer. And the second thing that it also means is that it cannot evolve over time once you deploy it. It's expensive. And the direct consequence of that is that because it is minimal, then it's going to be low level. And so developers can't use the network layer primitives for building their applications. And so that's this gap between the application layers, what it needs, and what the network layer provides. And so the function of transport is essentially to bridge this gap, to provide the application with higher level primitives to do whatever they want to. So let's look at today's transport, that is TCP. UDP is just a subset of that in some sense. So TCP provides reliable data delivery, which is like a point-to-point, this ordered data pipe. It provides multiplexing and demultiplexing. So essentially, instead of two hosts, which IP gives you, TCP provides this communication between two processes. It has congestion control, and it has this byte stream data delivery. So it is easy to use. You can't use packets directly. But there are some problems with each one of these. So first is that today's applications are distributed. And so we need communication between multiple processes, not just two processes. And the way we fix this is to build these application layer frameworks like MQTT or PubSub that let you do this distributed communication. And congestion control is also something, ideally, this should be done at the network layer. The reason we do it at the transport layer is because we can't do it at the network layer in IP. And finally, we have this byte stream data delivery, but that also has this one-size-fits-all problem. For example, head-offline blocking, which essentially quick solved, but it assumes that every application can use this efficiently. So now when we talk about transport in NDN, NDN already provides us with network layer congestion control. It provides us with application namespace demultiplexing, and it has this multicast data delivery. So initially, the initial NDN design did not have a transport layer protocol, and this need for transport was actually realized over time as we tried to build applications for NDN. But what do we need from this transport from NDN? The obvious one is we still need reliable data delivery. NDN is still a low level. It's going to be best effort datagram delivery. So, but now what we realize here is that the applications are distributed, and so we want it to be in the context of this multi-party communication. We don't need to do multiplexing, demultiplexing, or congestion control anymore because the network layer gives us that. We also need to still have some easier to use APIs because the applications cannot use these interest data exchanges directly. So that will be the function of the transport in NDN. And the way the NDN transport is going to be different from this existing TCP/IP transport is, first, it is going to be multi-party. Otherwise, why are we doing this in the first place? And because it is multi-party, then it needs to support heterogeneity. And what that means is when we talk about, for example, reliable delivery of data, then our definition of reliability is no longer the same as when it is between two parties. For example, if I produce an image on a chat application, then someone might not want that image, or some other device might be low on battery, and so they might not want to waste the resources to fetch that image. And so you will have individual constraints and preferences in this multi-party communication on who wants what data. So the solution that NDN Sync essentially is that we just tell everyone about what data is produced, and that really is the names of the data. And so anyone who knows that what the data is produced, then they can fetch it if they want it and as reliably as they want it. And so that is essentially going to support this heterogeneity. So the NDN transport, which is sync or distributed dataset synchronization, the function is to synchronize the names of the object produced inside the communication group. And this is done reliably. So everyone gets to know what everyone else has produced. But the group members, that whoever now knows that this data is produced, now they can decide if they want to fetch this data, when they want to fetch this data, and how they want to fetch this data. So essentially, the only function of sync is to do namespace synchronization, which is telling everyone what data is produced. So we looked at the designs of the previous NDN sync protocols, and we identified that there are actually, to design a sync protocol, you need answer these three questions. Or these are the three important points that we need to address in designing a sync protocol. The first is our local dataset representation, which really means how do you represent this dataset, which is the set of the names that are produced by the application. The second is how do you notify others? And so NDN is a pool-based architecture, so we don't have unsolicited data packets. So we cannot just, if someone produces something new and everyone else needs to know it, then they can just send out a data packet to tell everyone that I produced something new. And finally, we need to figure out when we send this notification, what do we actually put inside it? So how do we encode dataset changes inside it? And so I'll go over each one of these in detail for what we found. So for the representation of the state, there are two commonly used methods inside the sync protocols. The first is to just use a list of names to represent the state as a list of names that each producer has produced. So Alice produced some messages, some names of object data, and Bob and Kathy similarly. And so we just keep this as a list the way it is. The second way to do this is to use a sequence number. So we don't really keep the names of the data inside a data set, but we just keep how many pieces of data this particular producer has produced. So Alice has 2, Bob has 1, and Kathy has 1. And what this also means that our names then get constrained as being, you should be able to create the names of the data from your sequence number. Otherwise, you can't fetch the data. So these are the two types of state representation that we can use. The second one is more interesting, which is notification. When someone produces a new piece of data inside a group, then everyone else needs to know what that this new piece of data was produced and what the name of the data was. And you can't do something like periodically fetch it because you don't know when someone might produce a new piece of data. Now, the only unsolicited packet that you can send in NDN is this interest packet, and all the sync protocols implement this multicast sync interest, which carries some state and is used So this is actually used in two different ways. The first is long-lived interest, and the second is using the interest as notification. And I'll again describe each one of these in detail. So the first approach to do this notification in NDN is to use long-lived interest. So what that means is everyone sends a multicast sync interest to everyone else inside the communication group. And now they include some encoding of the sender state, whoever sent this sync interest. And this sync interest is kept pending at all the other participants. And as soon as someone produces new, then they reply to this pending sync interest, and then this data gets multicast to everyone else. So I have the simple example on the right, Alice, Bob, and Kathy. So Alice sends out a multicast sync interest, which goes to everyone. And similarly, Bob and Kathy send out their own multicast sync interest, which again go to everyone. And the steady state looks something like this, that everyone has a local pending sync interest. Now, if Alice produces a new piece of data, what Alice can do is simply reply to this multicast sync interest, and then the data also gets multicast to everyone else inside the group because they send their own sync interest. And now when this is done, then this is just going to vanish, and then they again send out their own multicast interest, so we are back to steady state, and this goes on. The second approach is to use interests themselves as notifications, and that really means put the entire protocol information inside the name of the interest or inside the interest packet, and then don't reply to it. So in this case, we have the same example, and Alice produces something new, then Alice will simply send out an interest packet, which is again multicast to everyone, and that's it. Then we just let this timeout inside the network, and we never reply. We put all of the information that we need for the notification inside the sync interest itself. The third question is about the state encoding. What do we put inside the notification? And for long-lived interests, there are two things. We have the interest itself, and we also have the reply. For the notification interest approach, we just have the interest. We don't have a reply. And all the sync protocols actually have their own unique design for this particular, so this is like the defining factor for different sync protocols. So what we did was we took these four popular sync protocols in NDN that were developed over time. So ChronoSync was like the first sync protocol that was used to build some application, and state vector sync is one of the most recent ones. And there are, so we took these four representative sync protocols for our comparison. And so all of them have some differences. For example, ChronoSync, psync, and state vector sync use sequence numbers. SyncPS is the only protocol that uses application names directly for the dataset representation. And the first three protocols use long-lived interest. State vector sync uses this second approach of interest notification. And ChronoSync uses state digest inside the sync interest as a representation of the state. SyncPS and psync use invertible Bloom filter. These were sort of, psync was sort of built on top of ChronoSync, improving on its what it lacked. And state vector sync has a new approach of using raw state inside the sync interest. So we discuss the protocols in detail inside the paper. If you want to know the detail how the protocols work, then you can refer to the paper. So I'll go straight to the evaluation. We actually put these protocols against each other inside a evaluation scenario, and we ran this inside mini-NDN with a 45-node topology where 20 nodes produce data on a sync group. And what we did was we varied the data production rate on the x-axis. So the x-axis is the number of data items published per second by the sync group as a whole. And we did this for two experiments, one without loss and one with 20% loss on each link inside the entire network. And we took two metrics. The first is the sync latency, which is how fast can you let everyone know what data is produced. And the second is the overhead, and that's in the terms of number of packets that you exchange at the end of the experiment. And so what we found was that state vector sync consistently outperforms all of the other protocols, and by a wide margin. So the green one is state vector sync, which has a lower latency, and it has a consistently low latency in without loss and with loss. And it also has a lower packet overhead compared to the other protocols, which is surprising because it has better performance in both metrics. So what we did was we tried to figure out why this is the case and what differences in the designs are actually enabling state vector sync to perform better compared to the other protocols. And so each of the three design aspects that I described earlier, they have their own lesson learned from this. So the first one is the dataset representation. So there is one more evaluation result that I did not display earlier, which is the reliability. So at the end of the experiment, when we produce some data, how much of the dataset was successfully, reliably synchronized with the participants. And what happens here is that all of the protocols except SyncPS have 100% reliability. And only SyncPS has actually a low reliability, which actually falls down to less than 20% at higher publication rates. The reason for this is that using the application data names in the dataset representation has some scaling problem that you have to get rid of. You cannot keep putting application names inside your IDF, and so you have to remove them after some time. And in this case, SyncPS removes it after 2 seconds. And what happens is that if you do not synchronize it within these 2 seconds, then that data is going to be lost and it's never going to be synchronized. So this essentially means that if you don't use this sequence number, or what we call the loss resilient transport identifier, then you will have some kind of problem like this. You will have to do some workaround, like removing the item from the dataset after some time, and that's going to affect your reliability. So if you lose some messages, then you might lose some state eventually. So this is the first lesson, that we need this resilient transport identifier for identifying what piece of data has been produced. The second one is this notification mechanism. So the problem with long-lived interest is that it cannot handle simultaneous publication. And this is shown by the evaluation results, where as the publication rate increases, then it's more likely that multiple participants are publishing at the same time, and then the performance drops for the protocols using the long-lived interest approach. And so the reason for this is that one Indian interest has only one data reply. And so when you send this multicast sync interest, then only one reply to the multicast sync interest is going to go back to the sender. And all of the other replies are going to get discarded inside the network. And that means that the sync group is going to be out of sync now, and now you have to have more steps to reconcile, and this is going to be slow. So taking the same example, if Kathy sends out a sync interest, it goes to everyone. And now if Alice produces a new piece of data, so Alice is going to reply to the sync interest. Now if at nearly the same time, if Bob produces a piece of data, then Bob is also going to reply to the same sync interest. And at this middle point now, the second reply from Bob is going to get dropped, and only the reply from Alice is going to go back to Kathy. And so now Kathy never heard about Bob producing a new piece of data, and now you need extra steps to reconcile this lost information. So this also has a second problem, that it has a bit higher overhead because you have these lost replies to multicast sync interest, and this is a waste. And you also have this PIT entry everywhere, and you need to keep refreshing this. But that's not that important. So for SVS notifications, on the other hand, each notification is independent. So when we send these interest notifications, they don't interact with each other in any way. And so you can actually handle simultaneous publications. And that is because you have no sync interest replies. You don't have a reply to a multicast interest in the first place. And that also, on a side note, that also enables suppression. So let's take the same example. If now this is a steady state for SVS. If Alice produces a new piece of data, Alice is going to send out a multicast sync interest. And if at the same time Bob produces a new piece of data, Bob will also send out a multicast sync interest. And now these simply propagate inside the network independent of each other. So we don't have the same problem. Kathy gets both pieces of information. So the lesson learned here is that this long-lived interest, especially having a reply to multicast interest, is a problem, because when we have reply to multicast interest, some of these replies are going to be lost, and then we have a problem. The third one is the state encoding. So the idea for using this kind of compressed encoding, which is like a digest or an IBF, is that we can have lower overhead or we can have better scalability. But what we see here is that when we use raw state, it actually carries more information. So now you need less messages. And so in turn, you have less number of packets, and so you have lower overhead. So so kind of the conclusion here is that you can use raw state, and it's still going to have, at least in terms of packet, we can see here that it has lower overhead compared to using some sort of compressed encoding because of the number of messages being lower. So to summarize, the lessons learned, again, we need a loss resilient transport identifier, which is the sequence number. And that really enables us to be reliable. So essentially, if you miss some data packet in between, some information in between, you see a later sequence number, then you can infer that the producer produced something before this as well. The second one is that there is a problem with long-lived interests, specifically long-lived multicast sync interest, which is the problem of having a data reply and the other replies getting dropped. And then we can have this better performance with raw state encoding, and also lower overhead because it carries more information. And so we need less round trips to reconcile any lost state or something like that. And finally, inside the paper, there is also further discussion on sync security and sync interest multicast itself, which is a major challenge. So for details on that, please refer to the paper. And finally, our future work in sync in general is for more formal definitions, say proof of correctness for sync. And like the work we did here was mostly experimental and trying to figure out what's happening. So we need a more rigorous theoretical analysis of sync. And when we're using raw state encoding, the second question is scalability, because it might be a question that is this putting the raw state inside the sync interest scalable? So that is part of future work. And finally, scalability of sync interest multicast itself, which is a general question for sync. So yeah, I think I'm done with the presentation. Thank you for listening.
Thank you. Okay, so any questions?
Any questions?
Now you can skip.
Thank you, great paper, Varun. I don't know whether this makes sense, but we have a concept of the network accepting instructions. If you've got a distributed content network, then the two obvious ones are publish, perhaps with some quality of service set of specification attached, and then subscribe, which is, tell the network to give it back to them, or give something. Have you thought it's kind of thinking about it from the other end of the telescope, which is really an API. It's a human API, obviously, and then you use names to do that. But it's also it's a system API as well. I don't know whether that makes any sense or whether you thought about that.
So we do actually have a publish subscribe API built on top of sync.
Yeah.
So sync is just a middle layer for there. You can build higher layers on top of sync, which will let you provide some APIs like PubSub. Okay. PubSub is actually.
I'm not talking about kind of the classic understanding of PubSub. I'm talking about where you as a user say, the example I always use is, Rett/Bondi/Batman/4K/director's cut, no API. And then that just goes out as an interest request into the network. Mm-hmm. It's translated. In fact, that's a subscribe request, and you put it directly into the network.
Yeah.
Yeah. Same concept.
Yeah. So actually, there's a poster in ICN 21 that talks about building a PubSub on top of state vector sync.
Okay, great.
Yeah.
Other question?
There's a bunch for me in the Slack. You can take them offline and answer them later.
Yeah.
Unless you want to take anything.
I don't have internet, so.
Well, there's one. Okay, so there's also one from Dirk. Long-lived interests. He says, don't they have some other problems in general? Yeah. So the general problem is that you have to have this PID entry, and you have to keep refreshing it the entire time as soon as it expires. That's a problem with long-lived interest. The problem I'm describing is for both, you have long-lived interest and multicast at the same time, then you have even bigger problems. Right, but even if, I think Dirk's point in his question is long-lived interest, you don't see it.
Weird. Oh, because I dropped off signing in.
State on forwarders, interaction with retransmissions.
Retransmissions.
They also might interact with retransmissions.
Yeah. So, I mean, there is a problem with using long-lived interest in the first place, but it gets aggravated when you multicast it.
Yeah, and another question, which I also have, is it seems like the assumptions on pretty much all of these is, well, maybe not the FPS, but the assumption is you have a local broadcast domain. And how do you do inter-domain multicast, right?
Yeah, so that's, like I said, it's multicast. Interest multicast is something that we need to figure out how to do it efficiently.
Or not do.
Yeah.
Actually, I would argue that interest multicast is a necessity. This is stated by Steve Darren in his 1988, the very first paper, SICOM 1988, very first paper on multicast. He pointed out that there are two needs for multicast. One is the efficient data delivery, data dissemination. That is what people considered as a multicast. And the second use of multicast is to the information dissemination. And he pointed out the current approach was like a directory lookup, essentially centralized server-based thing. And he pointed out that using multicast to push out the information is the most resilient and the simplest way to achieve this thing, to distribute information to a group of receivers whom either you don't know individually or you don't wish to identify them individually. In particular, this talking about the IP, location-based thing, to say some may be mobile and therefore it's hard to track. With multicast, the local joining something so that I make this tracking the movement to be a localized action. And so therefore, using multicast to disseminate the new information. It's really second use, but that second use seems after, let's say, 30 years, hasn't been picked up. I think that in doing
There's good reasons why it hasn't been.
it's unclear. But I think one good reason is because directory server is such a dominant concept that people thought that's the only way you learn about new information.
So I'll point out that Swinehart's original paper on this did not require multicast and worked quite well. Swinehart's paper on epidemic algorithms for distributing replicated data did not require multicast.
It doesn't have the real-time property.
Neither does this.
It does have, if you have multicast sync interest, then it will be real time because
No, it isn't.
I mean,
The car will still crash.
I mean it's the best
If
you
it
can
doesn't
do.
arrive in 35 microseconds, the car will still crash. It's not real time. Real time has deadlines.
Hopefully not the whole network crashes. Therefore, the next try will get there. So
We should move on.
the SPS is designed with resilient recovery from losses.
Okay,
It's
so
definitely the new thing we're bringing up. So like Varun put it there, it's like that in the future, the work will be fully exploited. I agree with multicast routing has been a challenge. We have some proposed directions to establish.
okay, so please continue in the Slack discussion in the Slack. Okay. So the next speaker. Okay, so the next speaker, the title is Dicer Distributed Coordination for Work Computations. And the authors are Uthra, Ambalavanan, Dennis Grewe, and others. Okay, so please, thank you.
Thank you. Hi all, good morning. This is Uthra Ambalavanan. I'm currently a research student at Robert Bosch and TU Munich. So today I'm going to present the topic of Dicer, which is distributed coordination for in-network computations. I guess pretty much everyone in the room already is aware of the basics of information-centric networking and the need for one. So the traditional internet was designed for host-centric communications by establishing communication between stationary nodes. And ICN kind of shifted this focus towards data and enabled end users to address data directly using their names and provided a loosely coupled communication model. So other features of ICN include flexible hop-by-hop routing, in-network caching, and multicasting, and so on. Name function networking is an extension to NDN, which is an ICN architecture, wherein NFN extends NDN by not just providing access to static data, but also to dynamically computed results. In order to do that, it uses the ICN principles or underlying NDN principles for transporting and delivering data. Consumers define workflows. These workflows are interpreted by the NFN resolution engine, and these resolution engine decide where the interest needs to be forwarded or what has to be done with the interest. The default resolution strategy for NFN is find or execute, which is FOX. And in here, the nodes try to interpret the workflows, identify the function and data components. If both function and data is available, then the node can start executing. If one of them is missing, then the nodes initiate a fetch operation to fetch the other. And if neither function nor data is available, then the nodes decide to forward the request upstream. So name function networking is an extension to NDN. It provides access to computation results. Of course, these kind of hop-by-hop decision making of NFN resolution engine is quite quick, and the amount of knowledge that NFN uses in order to make such quick decisions is restricted to the node itself. But this itself results in a lot of limitations and challenges in NFN. For instance, the routing is purely dependent on how the workflow is structured. Consumers who do structure the workflow are often unaware of the characteristics of data or function, and this could result in an inefficient routing. Similarly, the nodes make local decision making without being aware of the surroundings or the neighboring nodes, and which could also result in suboptimal decision making in terms of function execution and forwarding, as well as in function decomposition. So most of these challenges can be attributed to the reason that resolution in NFN is often done based on the local knowledge of the node. We introduced DICER, which is distributed coordination for in-network computing. In this case, we retain the NFN resolution engine at the forwarding plane at all compute nodes. And on top of that, we utilize or create a synchronization group wherein all nodes exchange information, gain the neighborhood knowledge, and improve or alter the forwarding decisions taken by NFN. So in this figure, in the slide here, you can see 3 nodes, A, B, and C. The queues next to B and C refer to the execution load at each of these nodes. And as and when B receives an interest for execution of function 1 on data 1, it decides to forward the interest upstream to node C, even if it has some resources to spare. And in this case, it would be much better for B to share the load of this computation rather than forwarding it to C, which is already loaded, as you can see from the execution queue. So with DICER, we expand this knowledge scope. So the brown shaded region shows the synchronization scope. So we group nodes B and C together, and B and C exchange information with each other and share the compute and network state. Now, after DICER synchronization, the node B is now aware of the execution status at C and therefore performs some decisions. One such decision could be to fetch the function 1 and execute the upcoming request for that specific function. So DICER is a combination of both NFN and the distributed synchronization or coordination. Along with this idea of DICER comes a lot of challenges. For instance, how do we group nodes? When and what kind of information do we synchronize on? How do we use the collected information for coordinating computations between nodes? And how do we handle the network overhead of synchronization? So in order to answer these questions, we derive the DICER concept, which is divided into 4 phases. So we have the neighbor node discovery, the synchronization group formation, synchronization, and coordination. In the upcoming slides, we look in detail into each of these phases. So with the neighbor node discovery, the agenda of this phase is to understand the neighborhood and the network topology. So we use the principles of NLSR, Name Link State Routing Protocol, in order to discover the forwarding nodes. So in here, the nodes periodically broadcast discovery messages, And in order to avoid the network overhead that can come out of it, we try to restrict the range at which these messages are broadcasted to a certain hop limit. And the nodes respond to these discovery messages. And as a part of this discovery message, it's not only to understand the network topology, but also understand the node characteristics or compute configuration of the nodes. Therefore, nodes also use this phase to learn the static compute configurations, such as CPU, RAM, ROM at a node, along with the network configurations, such as round trip time, the link bandwidth, path latency, and so on. So in this slide here, we have a network topology with 5 different nodes, and the table below shows the information collected at the end of neighbor node discovery at node 1 about every other node in its surroundings. The next phase is then the group formation phase. So in here, we define synchronization groups, and we use 3 parameters to define it. So VI, which is a set of nodes that form a group. TI is the synchronization frequency at which the nodes exchange information, and PI is the properties that the nodes synchronize on. Theoretically, it should be possible to group every node in the world into one big synchronization group, ensure that they are synchronizing at extremely small intervals and on extremely fine granular details, but this just renders the entire setup impractical due to the scalability conditions. And therefore, in order to ensure that the synchronization group formation is both scalable, but minimize the loss of information by restricting the size of groups, we come up with employing multiple synchronization groups. And within these multiple synchronization groups, we vary or tune the size of the group, the synchronization frequency, and the information synchronized. So in this figure here, you can see that around node N1, which is at the center, it forms or becomes a part of 3 different synchronization groups, SG1, SG2, and SG3. When we talk about SG1, the node is connected to other nodes 1 hop away, and the shade of gray shows the amount of information that the nodes synchronize with each other. So SG1 has less number of nodes, more fine granular detailed information synchronized at much closer intervals because N1 needs to react faster to the changes in the neighborhood. Whereas with the case of SG3, here we increase the number of nodes in the group and so spread out the scope of synchronization. And in order to ensure that it is still scalable or the network overhead does not go beyond, we try to limit the information that we synchronize to only the crucial information or an aggregate information. And this synchronization does not have to happen on very close intervals, as it is only the crucial information that is being transferred gradually across an enhanced distance. So with synchronization group formation, we have the following terminology. So every node initiates a group formation proposal prefix or interest with a group formation proposal prefix, and the other node receiving such interest would then respond back with another interest asking for the details about the synchronization group proposed. So the information could be what are the members of the group, what kind of information is being transmitted, what is the synchronization frequency, what is a agenda behind this group, and so on. So once the node gets these information, they can either agree to this invitation and join the group or send a negative acknowledgement back. So of course, we also go with there's also need for a group optimization phase within the group formation phase, and the purpose of this is to avoid any kind of redundant information exchange between the nodes belonging to multiple groups. You can see, I can give you an example of that with the example network topology with 5 nodes. So let's assume that group formations are proposed from node 1. It forms a 1-hop group with node 2 and node 3, and a 2-hop group with node 4 and node 5. Similarly, at the same time, with node 4, it also proposes 1-hop groups with node 2, 3, and 5, and a 2-hop group with node 1. In this case, you can already see some kind of redundancies. For example, the 2-hop group from node 4, which comprises of node 1 and node 4, already is a member of another 2-hop group, which is a bigger group. So it is the 2-hop group from node 4 is a subset of 2-hop group from node 1. So therefore, there's this redundant synchronization which can be avoided. Similarly, the groups from the one-hop groups, which comprises of node 4 and node 5, already share fine granular information in the one-hop group, and therefore they would not want to fetch the crucial or aggregate information from the two-hop groups at node 1. So such kind of redundant information exchange in groups are eliminated as a part of group optimization phase. So it helps to curb the network overhead that arises out of synchronization. The next step itself is synchronization, and as a previous presenter, Varun already emphasized on how SVS is much better than the other synchronization protocols. We also agreed to that and decided to use state vector synchronization for the process of synchronization. And in here, SVS was initially used for application dataset synchronization, which was utilized for chat applications such as NDN chat. And it uses this vector-based data model. So maybe I can go briefly through the slide because Varun already presented most of the crucial aspects of SVS. So in here we have three nodes, user A, B, and C, forming a synchronization group, and the state change is attributed to a sequence number. So the latest state change at user A changes from 50 to 51, and this needs to be propagated to user B and user C. And they do this by using a sync interest with the group prefix as well as the state vector. And every other member of the group would compare the state in the state vector to the local state, source state in their data store. So user B and C have the state 50 stored in their data store, whereas in the sync notification, you have the state 51. So user B or C would then decide to fetch the changes corresponding to sequence number 51 from user A by sending a follow-up fetch interest. So that's how the nodes within a synchronization group synchronize with the state. We implement, as a part of implementation, we implement two types of synchronization groups. We have a one-hop synchronization group where nodes with their one-hop neighbors are grouped together, and we refer to this as a zone. And the kind of properties, nature of properties synchronized within this one-hop group includes node resource utilization, the functions instantiated at each node, the list of unresolved compute requests at each node, functions hosted at each node, and so on. And the other synchronization group type is a three-hop synchronization group type, which expands the distance of synchronization to more than one hop. And in here, since the number of nodes which should be grouped within this group is going to be higher, we restrict the properties synchronized to just the crucial elements. For instance, we take the zone's average resource utilization, or the most popular function at a zone, and or the most unresolved compute request at a zone, and so on. And we synchronize the one-hop synchronization group at twice the interval, or twice closer than the three-hop synchronization interval. So the fourth phase and the final phase is the coordination phase, wherein we use the collected information and try to make some changes locally. So based on the information collected from the synchronization groups, the nodes go through the coordination phase, wherein they decide based on their compute capacity. So they see if they have compute resources available to support the other nodes in the network. If they do, then they try to find out the most popular unresolved function from the surrounding zone or the neighboring group. And in order to ensure that most popular unresolved function is handled first, we kind of sort it in a descending order and try to instantiate as many functions as possible. And this goes on as long as the resources can be spared at the free node. If, on the other hand, the node itself is not free, then it just decides to terminate any least popular function that it can identify and terminate the coordination algorithm. So this concept of DICER, so all the four phases have been implemented using and evaluated using the network simulation environment NDN Sim. This is the evaluation setup that we use. So we are evaluating it against a three-tier hierarchical topology with compute nodes ranging from 3 nodes to 35 nodes and consumer nodes 100. The number of unique functions itself is ranging from 100 to 700 different functions, and those would be the function characteristics of the functions. And we also try to evaluate on the scalability of synchronization by tuning the synchronization interval, starting from 2 seconds up until 50 seconds. And all the simulation duration would be then 1000 seconds, and the results following up are a result of approximately 250 runs. So the first evaluation metric is the orchestration map. So orchestration map can be defined as the placement of functions at different nodes in the network. We evaluate the performance of DICER against both NFN to see how better it is to NFN, as well as with NFID, which is the next fit decreasing algorithm. So the next fit decreasing heuristic sorts the functions based on the request popularity and places them from nodes closest to the consumers. And NFID does not replicate any functions based on the popularity. So that is also a reason why it has the ability to place more functions when compared to DICER or NFN. Using this as an upper bound, we can see that when we compare the orchestration maps generated from NFID, NFN, and DICER, we see that DICER is almost 2/3 similar in placement when compared to NFID. In here, the performance of NFN is degraded mainly due to the reason that we are using an imbalanced load profile, wherein part of the network is or the compute nodes are highly loaded, facing a lot of compute requests, while the rest of the compute nodes are pretty much idle. And in one such scenario where NFN's knowledge does not extend beyond the local scope, it does not contribute much by instantiating functions, popular functions of the neighborhood. Whereas DICER kind of detects the popular functions as well as and places them, as well as detects the free nodes and places those popular functions on free nodes, establishing a load balancing effect. Additionally, in DICER, since it looks into unresolved requests, it also handles replication of popular functions, which is currently not done by the NFID. The next metric that we evaluated was the completion time. So completion time can be defined as the round trip time between compute request initiation and the response received by the consumer. So on this slide, we can see two graphs. On the x-axis, we have the number of functions, unique functions, and on the y-axis, we have the service delay experienced. We modify or we test it on different load profiles. So when in a completely balanced load profile where all compute nodes receive some kind of compute load, that is when IBF is equal to 0, there is not much of an improvement that you can see from DICER over NFN, because NFN itself does pretty good job in identifying and instantiating functions that are on path. However, in an imbalanced load situation where IBF is set to 1, where 50% of the nodes are loaded and 50% of the nodes are idle, we can see some improvement in terms of completion time with the presence of DICER. So this kind of gives us an idea of where and what kind of situations can DICER be switched on and when it does not add too much of an improvement. The next evaluation metric is the scalability test. And of course, we have this periodic synchronizations and periodic node discoveries phases that we use in our DICER concept. And we need to test how far is it scalable. And we evaluate it against the size of the network as well as the synchronization interval that we use. So on the x-axis, we have the increasing number of compute nodes, and on the y-axis, we see the traffic load generated by just the synchronization alone. And with both increasing number of compute nodes as well as with reducing synchronization intervals or much frequent synchronizations, the overhead of synchronization is actually showing a quadratic relationship. And this can be, to an extent, there are ideas to mitigate this synchronization. So group optimization was one way wherein we avoid redundant synchronization. Another option could be to employ partial synchronization, wherein only the most capable node or the most connected node can perform synchronization and learn the neighborhood so that it can contribute to making decisions and enforcing decisions in the zone, instead of every node receiving all the information. One could also use some data compression techniques while doing desynchronization, especially while doing fine granular close synchronization in one-hop synchronization groups. So the example with one-hop or hop-based synchronization is just an example that we used to evaluate the concept of DICER itself, but there can be other ways in which we can technically group nodes together. One way could be to group nodes instantiating the same function, so that when one of the instantiations or nodes face a high load for that particular function, the other nodes can automatically assist the nodes and bring up a load balancing behavior. So that brings to the conclusion of my work. Summarizing, we had a short presentation or a brief presentation about the default resolution strategy in NFN and its limitations, presentation on the concept of DICER for ICN and the SVS synchronization protocol, and finally the simulation runs and evaluations that we obtain out of comparing DICER with NFN. As a part of future work, we intend to enhance the orchestration algorithm, which is currently pretty simple, and it can be improved with having an objective of joint optimization of both compute and network resources. At this point, it just focuses on the compute resources. And the current coordination also only takes care of the function placement, so it can be further improved by taking into consideration of both data and function distribution in the network. Imparting security is also another important aspect that has to be included into DICER, especially when we look into scenarios where we group nodes across multiple administrative domains. So that brings the conclusion. Here are the references used in the presentation. Thank you, and I'd love to have some questions.
Thank you. Question?
Thank you for the very good talk. I have a question regarding the function placement. You said that DICER somehow places the more popular functions at idle nodes, but it's not using something like least frequency used, like in the caching world, where you say least frequently used items are automatically placed at nodes further away or something like this. So how does this exactly work? I didn't fully get it. So how does the function, my question is, how does the function placement work, or how does it find idle nodes and automatically kind of places the more popular functions on that node?
What DICER does not enforce decision on other nodes, but makes local decisions or local changes. And in order to make these local changes, it uses the information that is gathered from the surrounding nodes. So from the surrounding node, it does get some information such as the resource utilization at the other node, or what is the most popular function that was also most unresolved at those nodes, based on the interest count, but no data returning back from the node, either because the resources were blocked and the interest was in queue and the interest expired before the node could react upon it. So it clearly denotes that the neighboring node is unable to handle the compute load for that particular function. So each node can detect this kind of a behavior from its surrounding and make local changes by fetching the function by sending another fetch interest and instantiating that function, so that any upcoming interest can now be shared between the nodes, since the routes would then be updated.
Yeah, I guess my question was, I fully understand that because of DICER you get that knowledge from other nodes. My question was, are you using a concrete algorithm like in the CDN world on function placement, or is it just kind of implicitly happening somehow?
We are having this coordination algorithm, which is currently very simple. So I try to just aggregate the information collected and try to sort it and do the fetch those functions which need the most help. But of course, this is a simple algorithm and it has to be further improved, which is also part of our future work. And in that case, as you said, we also need to take into an optimization goal, wherein we can decide. So currently, we see that with this algorithm itself, there is some kind of reduction in completion time, but that was not the optimization objective of this algorithm. And once we include such algorithms in the coordination phase, I think the performance of DICER would further improve.
Understood. My recommendation is, if you do work on that item, to look into the literature on cache placement and distributed caching systems, because there has been a lot of work on it, you know.
Yeah, I think off-path caching is very close to what we see here, because DISA is also trying to find or instantiate things that are off-path to the natural route to the producer. So off-path caching is actually a good starting point. Thank you.
Other question?
So I think you look at utilization, you're exchanging information about utilization and which functions are being, what, for your evaluation, what did you assume that all functions like take the same running time, or what did you actually use?
So this function popularity was changed by using a Zipfian distribution. So 20% of the functions were more popular than the rest.
I mean, okay, so you didn't take into account, for example, the running time of a function at all. They're all just functions.
No, the function execution duration here is changed or randomized between 2 seconds to 6 seconds. Okay. So we have to an extent of how, just to show short running versus long running functions.
That was what I missed. I couldn't see all that.
And we also wanted to see how it was affecting the synchronization interval, because when more number of 6-second functions are running at the neighboring nodes, then the information would take another synchronization cycle to get this information out. Yeah. Alex, you had a question?
Yeah, so the question I was having more mechanical of how exactly the redirection to the node working. I understand that in the vicinity, in the sync group, you can detect which node is available for the incoming request. You need to send that processing there. But how is it done?
Sorry, I did not get your point.
And the routing or forwarding will bring the interest to the node that not necessarily will have the opportunity to process. So in your system, how do you redirect the request from you to someone else to do exactly the same stuff?
Currently, we do not redirect interest that a node already receives. We just update the routes such that the intermediate forwarders kind of perform this load balancing in the best route strategy. So we ensure that the cost is comparable, and therefore once the route to a particular best route fails, then the next best route would be chosen by the forwarder.
But then that would depend on from where the interest is coming from, or you kind of the node that is not capable completely removed from the routing. So the routing is constantly updated that there is only one node that is doing processing. The next function.
No, the routing is updated such that more instantiations of the same function is available in the network. And so since we're also doing this distance-based synchronization, it is just one hop to which this interest has now needs to be forwarded.
I mean, one hop is very limited, at least for the evaluation scenario. I think it's more valuable to have a bigger environment, not just 1 or 2 or 3 hops, but the bigger. Let take that away.
Mm-hmm.
Okay, thank you. So if you have more questions, please put your comment or question in Slack.
Yeah.
Okay, thank you. Okay, so the last speaker, you will. Okay, so yes, please.
Should I start?
Yep.
Okay. Timer. Just a second. Okay, so this one is about, I'm going to presenting this distributed object store that we built over NDN again. And this is, I want to say that this is an initial attempt to build such a distributed data storage over NDN. So it's an initial attempt. Just want to mention that. And so I'll start with why do we need storage in NDN? And this is like asking the obvious, that because we generate a lot of data, and with the data-centric model of NDN, with data-centric models of everything, IP systems miss these supporting functions that we desire, like a data-centric security model, or in-network caching that you might want for higher performance, or multicast of data. And so we can achieve this if we build a system over NDN for data storage. And so this work is about that. Like I said, it's an initial attempt to build this high volume data store NDN, and high volume directly means that it has to be distributed. So before we start building any system, then we need to ask some questions for who are we building it for, because we can build it for every use case. So the first question is, who is the storage for? Is it single tenant, multi-tenant, or is it like a community storage, maybe like IPFS, and who runs it? The second thing is, how much they store? Is it single node, which is actually most of the existing data stores over NDN, or is it distributed? If it is distributed, then how many nodes? Because we can't design a system to scale infinitely. And the third is, what should be the security model? Should the store provide some security like the existing data stores, or can we do some kind of application-defined security? And finally, what interface does it provide to the application? Like, is it a database, file system, object storage? And so I highlighted the decisions that we chose, the intended users, that we make it a single tenant, distributed store, but with, again, not infinitely scalable. And then we try to have this kind of application-defined security model, and we make it an object store. So identify the goals of why we're building this. The most important one is that we want to simplify the design. So we want to simplify the design of both the store itself, data store, and the application that is using this data store. The second one is that we want to have automated operation, minimal configuration, plug and play, and automated failure recovery if a physical node goes down. The third is it should be easy to use, reduce application development costs, and finally provide good security for access control and confidentiality. All data stores need that. So to design a data store, we need to ask these three questions. The first is, what do we store? And what I mean here is, what is the addressable unit of the data storage? Is it a block of data, a file, like in a file system, or is it a chunk of some chunk of some kind of data? Or do we address like the whole object as one single piece of data? The second question is, where do we store the data? And that really means if I get a new piece of data in a distributed data store, where does this particular piece of data go? And to make this decision, we can, for example, use a central node, or we can use some kind of distributed algorithm. And in case our data store has some kind of replication, then we also need to decide which nodes, the multiple nodes where the data goes. So this decision of where does a new piece of data go. And the third one is how to locate this data. So if the client wants a piece of data from the store, it needs to know which physical node the data is in, and then it needs to get the data from that node. At least in IP systems, it works this way. And so to achieve this, we can do something like ask a central node, or again, use some kind of distributed algorithm to find out where the data actually is. So I'll go over each one of these questions in detail in the next few slides. So first question, and the answer that we use, what to store. So the applications it's an object store, so the applications have to deal with objects. These are basically just binary blobs of data. They can be at any size, and so we'll chop them up into smaller packets when they are being transmitted across the network. And because if they are Indian packets, then all of the packets will be signed, for example. Now, what we use as the smallest addressable unit is this data packet itself. So that is the same data packet that the application generated from this object, and we just use this as our addressable unit inside the data store. And so that means that there is no separate stored namespace, for example. And this is for our goal of simplifying the logic, that we don't have to do any kind of interaction. The second thing is that this data packet is going to carry the producer's signatures. It is going to be the exact same data packet that the producer produced. And so that means that it's going to be secure. If we store this data packet directly, it's going to always have the signature. It's going to be encrypted, whatever you do with it. Finally, we can use in-network caching. This will become more obvious later. The second question, no, this is still the first question. Okay. So this is second. Second question is where to store the data. So if I get a new piece of data, then which physical node it has to go into. To solve this problem, we divide the application namespace into these n buckets. And this is not a new concept. This is an existing thing in many IP systems. So to do this, we just take the consistent hash of the endian packet name. And then so if we have a fixed number of buckets, let's say 32, and we take a hash of the name, we take modulo 32, and we get a bucket ID. And then this data packet goes into that bucket. Now, we want, because we have replication, we need that for failure recovery. So we will have multiple nodes that are assigned to store each bucket. And then, so the question really becomes, how do we assign these buckets? And that is going to determine which node is going to store which piece of data. So to answer this question of how to assign, instead of using something like a central controller, we designed this kind of simplistic protocol called the auction protocol. And that's really straightforward. We take a bucket that doesn't have enough replicas. We ask everyone, whoever can store the data, we ask who wants to store this data, and then we just give it to whoever wants it the most. And then we keep repeating this. So this will terminate at some point because all of the buckets will have enough replicas. And then the question here is, how do the nodes say who wants this the most? How do we determine this wanting of the bucket? And for that, let me first quickly describe the protocol itself. So we have this auction master node. I want to emphasize this is not a single point of failure. It's just ephemeral. It exists for a few seconds, and it doesn't carry any state. So if you lose it, it's not a problem. So this master node is going to auction these buckets over S2S PubSub. And the way it is going to happen is it says that I want to give out this bucket. And then every node is going to send back a bid. Whoever gets this auction message, which is everyone. And they're going to bid, which is going to carry a dollar amount, for example. The auction master will collect all of these bids. It will see that who are the top, say our replication factor is 3, then it's going to collect the top 3 bids, tell them that you won this bucket, collect an acknowledgement from the winners that they know that they won this bucket, and finally send out a message saying that the auction ended and these are the replicas for this particular bucket. So again, the question here is now, how much do you bid? If a node gets this auction message for a particular bucket, the hard question to answer is what amount to send inside the bid. So that's really a central part of this auction protocol, which is the bidding function. And to bid, the node is only going to look at its local conditions. So for example, it's going to look at how much data do I store for this bucket? So that, for example, if a bucket is being auctioned and a particular replica already stores this bucket, then it's going to bid a much higher amount for that bucket. Because if it doesn't do that, then it's going to lose that bucket, then it has to go to someone else. What this gives you is steady state stability. That means you auction a bucket and three replicas already exist. The same 3 replicas win again, and so you don't change anything. The second thing that you might want to consider is how much have I already stored? For example, how many buckets have I already stored? And this is going to give you equality in the distribution. So if there is an auction and one node stores 5 buckets, a different node stores 10 buckets, neither of the 2 nodes store this bucket that is being auctioned, then the node that stores 5 buckets is going to have a higher bid because it wants to have the data more because it's storing less data in the first place. So this will ensure that our buckets get equally distributed among the nodes. The third question, the third thing that we want to look at is how much resources do I have? Because the nodes might be heterogeneous. Some of them might have more storage. So this is going to be the third one, that whoever can do more, they're going to store more. And so there is a lot of discussion on this inside the paper. For more details, please refer to that. So one more thing that the auction protocol gives you is failure recovery. So for example, if a node fails, then there are no longer enough replicas for any bucket that is stored by that node. So someone else is going to win in the next auction for that bucket. And that someone is going to be whoever wants the data the most, which can be by virtue of, for example, storing the least amount of data or having the highest amount of free space. And so when that happens, it's going to initiate a transfer out of the previous replicas into the new replica, and that's going to eventually restore steady state. Again, more discussion is inside the paper. The last question is how to locate the data inside the data store. And what this refers to is we already stored the data, or we also want to store the data, and the client wants to get the data, then how do we do that? And for that, we just use endian routing and forwarding instead of using some kind of DNS stuff, as IP systems often do. So what is going to work is every node is going to register 2 prefixes for each bucket that it stores. So if a node stores 3 buckets, then it's going to register 6 prefixes. So the first one is going to be like a cluster prefix, which is actually used for all communication with the client. So that's the this one, the top one. And the clients only know this QA prefix as the prefix of the storage. And the second prefix is going to be for internal communication inside the cluster. And both of them are also going to have the bucket ID for the bucket that this is intended for. So we have to register this for each bucket that a node stores. So to locate the data at the client, there are 2 things. The client has to know the cluster prefix. That is like the minimal configuration that we need, the name of the data store itself. And the second is that it can calculate the bucket ID from the data name, because it's simply a consistent hash. And you also need to know the number of buckets. But once you have that, it's just a hash and a modulo operation. So with these 2 things, we can actually do all of the storage and retrieval stuff. So let's look at insertion first. If someone wants to put an object inside the store, the client is going to send an insert interest, which is going to be the cluster prefix pre-configured into the client. Then it's going to do bucket ID calculated from the data name, the packet name that the client wants to insert, then the keyword insert, and then the actual data name inside the name of the insert interest. This is going to go to the nearest node that stores this bucket, because only those nodes are going to register this prefix of /QA prefix /bucket ID. And so it gets anycast to the nearest node that is responsible for this bucket. This node is going to then duplicate this interest and send it to all of the other replicas. The reason it knows the other replicas is because they were mentioned in the auction end message. And so here it's the steps number 2 and 4, where node 1 duplicates this client's interest to node 2 and 4. And now all of the replicas are going to fetch more or less at the same time from the client the piece of actual data, that is the data name. And because of in-network caching and interest aggregation, this data gets multicast from the client directly to all of the 3 nodes. And when this is done, the nodes 2 and 4, which are the replicas, are going to return an acknowledgement to node 1 that they stored this data. And node 1 in turn is going to return an acknowledgement to the client that this data was successfully stored. And that completes the insertion process. So about retrieval, how to get this data, it's even simpler. You just send out an interest for the actual data name, and you just attach a forwarding hint with it, which is the cluster prefix and the bucket ID. Once again, this interest is going to get anycast to the nearest node responsible for this bucket, because only that is going to register this prefix. And then if the packet was inserted previously, then it's guaranteed to be here inside this node. And so all it can do is simply reply to it. And if the packet was not inserted before, then the node knows that it's going to be nowhere else. And so it can just send back a NAC or something. So this is the way retrieval is going to work. The outcomes of using such an object protocol for insertions and retrieval has these effects. First, we can use data multicast in network caching, both for insertion and for retrieval. For insertion, we use multicast for getting the data into the store. For retrieval, if 2 clients send the interest for the same piece of data, then it just gets multicast from the store. The second thing is we have low latency, especially for reads. So 0.5 RTT is guaranteed. If the node, I should say 1 RTT, not 0.5. If the nearest node has the data, then it has the data. There is no further redirection of requests or anything like that. The third is that we have these meaningful signatures on packets at all times, which simplifies the security aspect in many ways. We don't put together the packets into forming some file or something at the server and then returning it again. I'll talk about this later in the next slide. And we also have strong consistency. So because if an insertion completes and then we send out a fetch, once the client receives an acknowledgement, all the 3 replicas exist. It's guaranteed to, any subsequent read requests are guaranteed to complete. And finally, it provides a very simple API. And this is in regard to the goal of making applications easier to develop. So for the security part that I mentioned, the individual data packets are again preserved, and that means that we can use any existing end-to-end security framework without reinventing the wheel. So for example, we can use name-based access control to do access control, and so we don't need any kind of gateway or access control to access the storage itself. We just encrypt the data packets themselves, and anyone can fetch them, but only who should be able to access them will be able to decrypt them. And then we can also verify the producer's signatures directly because we maintain them inside the data store. And so that means that the client never needs to trust the data store. The data store is just a dumb store. And this is true always inside the network as well as when you fetch the data. Finally, we did some optimizations. If you're listening, then you might have noticed we insert one data packet in every request. So that's going to be extremely slow. And so we have some optimizations for that. Also for storing the related data packets together. For example, here we have, for example, 4 data packets going into the same bucket because they are sequential. Typically, our objects are going to be large and they are going to be segmented using Indian's naming convention. And so we can exploit that to put chunks of data inside the same bucket. So we can do optimizations so that faster reads by caching locally. And finally, for the overhead of signing every packet, we can use something like signing manifest. Once again, please refer to the paper. There are details on these optimizations. Finally, we evaluated our implementation against Redis Cluster. And so we have an analytical comparison with HDFS, which really talks about how HDFS has a single point of failure, central controller, all of that, and this system doesn't. But we also have this experimental comparison with Redis Cluster, which is mini-endian, by the way, not endian sim. What we found was that obviously Redis has a much higher throughput, and that is because it's so mature and NFD is not very fast, which is what we use. But the overhead is, as expected, it's lower. And surprisingly, actually, in our evaluation, we found that Redis Cluster, the order of magnitude of the throughput is actually similar, which is actually surprising considering how mature Redis is. Who knows? And finally, the future work, we need to further work. There's a lot of discussion in the paper on failure recovery, how it's going to work, but we haven't implemented it yet, so we haven't tested it thoroughly yet. And we also need to figure out more storage backends. The one that we currently use is just a simple, because we're comparing it with Redis Cluster, so that's also a memory-based storage. We also need to do some more security framework integration, because while we can use security frameworks, but we need to make it easier for applications. And finally, we need to have accountability, like who can store inside the storage. And there is a starting point for this by signing the insertions that change state. But again, this needs implementation and more thought. So that's our future work. And I'm done. Thank you for listening.
Any question?
Yeah.
So I'm trying to convince myself that a client can't enlist the Q assistant to mount an amplified reflection attack against the original producers.
The client can, yes. So that is true. That's why, actually, something I did not mention here, this insertion is signed. This interest is going to be signed, and so you need some kind of, because not everyone is, again, I mentioned earlier that this is a single tenant system.
Which interest is being signed? The interest that's constructed by Q to fetch the
No,
data?
this is signed by the client.
Yeah, well, yeah, but I mean, so I just arranged to have a Q system that likes me and use it to mount a reflection.
I mean, the worst you can do is it's going to be like your number of interests are going to be replicated by the replication factor. That's what you can do. And what we can have something like, if you're sending too many requests, then you can throttle that at the first node. But yeah, in some sense, you're right. You can, if you just don't control the number of interests that you're sending out, then you could do a reflection attack with this.
Thanks.
One thing you said, so client will contact node 1 first. And then if node 1 doesn't respond, or if node 1 sends an ACK, then it's not going to forward that interest again, right? For the content.
For are you talking about fetch or in fetch? Yeah.
So what happens if the node 1 fails? Like if it does not respond or something like that happens, but it had already replicated the data in the past while inserting it. But during the fetch, the node 1 is not responding. What happens to that insert?
So if node 1 fails, then it's up to the routing to figure out that this route is no longer reachable. So the routing we expect that the routing will converge at some point, that the interest will then get anycast to some other replica.
But you said that if node 1 is not sending, it's sending acknowledgement or something like that, it's timeout or something, it's not going to call that thing again. It's something like that.
No.
Addressed to the bucket, it's not addressed to the node, right?
Yeah.
Buckets are replicated.
Right, but-
It's like any cast.
It's anycast, yeah. So I mean, what I said here was that if the packet was inserted, then node 1 has it. And if it was not inserted, and if node 1 doesn't have it, then it was not inserted. That's what I'm saying.
Okay. So which means if it somehow doesn't respond, then you will leave it up to the routing to.
Yeah, routing will just figure it out, send it somewhere else. Any other questions?
I won't ask about delete.
The what?
I won't ask about delete.
Delete. Delete.
I didn't ask about delete.
So,
So what's the, is this all for free? Is this gonna, do you think about an economic model for this or what? What's the incentive of the KUA?
Good question.
like I said, it's an initial attempt to build a data store over NDN, see what we can do. And again, this is a single tenant thing. So the idea is if you're building an application over NDN, you need to store the data somewhere. If you're building it for your whatever enterprise, and then you can use something like this.
Well, I guess one motivation for that question is what's the semantics? You're obligated now to store this data forever and ever. Oh man, he didn't ask about delete, but
no, it's so there in the paper. There's actually for practical reasons we have delete, so we can just send this. It looks exactly the same. It just has insert replaced by free, and so that means that it's going to free up the storage space. Of course, it's not going to guarantee that the data is gone because it could be in the cache or something, but it's really up to the application. And so, like I said, accountability is a part of the future work that we need to figure out who is storing how much, for example, and then maybe clear something that is old.
So I think I understand the nice properties of load balancing and spreading. Did you think about affinity? In the sense that guaranteeing that if there's a large number of objects that are semantically or fate shared related, that a given replica inside Q is guaranteed to either store all of them or none of them. So that when your failure semantics for your individual Q nodes don't have bad interactions with the fate sharing of the actual data.
I'm
thought about that at all?
I'm not sure I fully understand the question, but
what you're trying to achieve load leveling of all the individual atomic objects across the replicas.
Right.
Right. And I'm saying there's another metric that may be important, which is an affinity metric, that not all objects that you want to put in the store completely independent of one another. There may be some critical set of objects that all have to be available at the same time.
But it's not clear
that are fate shared.
What is that going to buy you other than if nothing fails?
If nothing fails, well,
what does it really buy you?
Well,
it's not like a hardware cache where you're going to prefetch. You're going to load some stuff in and amortize the expensive one over the future one.
I'm thinking more of the resilience question.
Okay.
Of under failure modes, what's the likelihood I can actually get all the critical objects that are fate shared?
I don't think this one considered that. Let's really take each object as a unit and replication, not inter-object replication. That's not in the design. And also, I think someone asked about the economical motivation. You mentioned this But now it's for enterprise. For example, hospitals, they need to store things. They wish not to upload to cloud, so this enables enterprise control the storage. Next API.
Yeah, so when you are inserting the data, as you said that there is a high likelihood that it will be segmented, and you have segments of data. So
Right.
doing a pre-deterministic kind of algorithm, running it, and then determining that you're going to get another segment Y after this. So try to.
Yeah, so that's the optimization I mentioned. For example, if you're fetching an object, it's likely that you might fetch the whole object. And so if you get a request for segment number 1, might as well be useful to cache the next 5,000 segments. Yeah. So that's something that we can do as long as we store the 5,000 segments on one node.
I think that it should be one of the basic properties that most of this system offers in this state. Otherwise, it will be very hard. Right? Yeah. If you are storing the current multimedia map.
If there are no more questions, then I'm done.
Okay, so let's continue to discuss in Slack. Yeah. Okay, so that's all for this session. So let's upload our speakers. Thank you so much. Okay, so now's the time for lunch. And
I think Toto sent the message saying the next session will be 11:45 in here.
Here?
Yeah.
Okay.
So it starts in 15.
So we don't have lunch.
That's the word.